All right, so let's jump in here and let's talk about this a little minute, since apparently my timer's not working. Alrighty, so bless it. So it tells us that Baumgartner's in free fall for 4 minutes and 20 seconds, so 360 seconds before he deploys his parachute at an elevation of 84 or 8,000 some odd feet. Okay, how we find his vertical distance of his free fall? What would I need to do? Aiden, what did you do to find the vertical distance of his free fall?
Take the 127,850 feet
Yep.
and subtract 8,420.
Yep, that's exactly what we do. And so before he deploys his chute, he's going to fall 119,000 feet. Y'all, there's no way I'm doing that. Just saying. Okay. So then let's find his average velocity during that time. Okay. So we know how far he fell. We know he fell for 4 minutes and 20 seconds, which would be 260 seconds. And so how would we get his average velocity? All right, what is velocity? Yeah, change in distance over time, okay? It's his speed with some direction, all right? So we know which way he's going. So the change in his distance was 119,040. Why did I make it negative? Because he's falling, all right, over 260 seconds, which gives us an average velocity of negative 459.346. What would his units be? Feet per second, okay? So units, as we have said before, are important to us. So there we go, okay? So he's falling fast, in my opinion. It makes me want to vomit. I would need a nausea patch, okay? No way I'm doing that without some medical intervention, okay? So then we jump over to, any of y'all think you could do it? Like you could free fall that far and be okay? Yeah? Okay. Marshall, you think you could do it? You think you could? Okay. Yeah, it would not be my choice either as well. All right. So they give me a graph of his elevation in feet above sea level, T seconds after stepping off the balloon. And then they give me a function. There's probably a reason they gave me that. I'm going to need it in a little bit. All right. So they give me f of t when t is between 0 and 50. All right. And 50 seconds. And they give us the graph. Okay. Was he traveling at a constant? Well, first of all, let's label this graph because they didn't tell me a whole lot. What would be my independent variable down here on the x-axis? Oh, yeah, that's my time, which would be measured in seconds. And what about our dependent variable over here? What's it showing me? Yeah, his height or his elevation in feet. So that's important so we know what we're looking at. Was he traveling at a constant velocity? No. Okay. How do we know that? Yeah, the graph gets steeper. So if we're looking at the slopes, the graph is getting steeper and steeper and steeper, so we don't have a constant rate of change. Okay. When do you think he would be traveling the fastest? Yeah, around 50 seconds based on what we could see near the end. Right? Because that's where we would have the steepest slope. All right, if we look at the slope of the graph where he first steps off the balloon, there it is. But if we get over here, it's much steeper. All right, that graph has got a much steeper slope. Okay. So then they asked me to do some calculations, and here's where we're going to use that equation that they gave me up there at the top. It's a lot, but it's all good. And they asked me to find his velocity between around 30 seconds, okay? And they start with the average velocity between 20 and 30. So we're going to do f at 30 minus f at 20. over 30 minus 20. So we got some big numbers. Y'all get these? 450 minus 121, 450. All of that divided by 10, we get negative 800 feet per second. Is that what you got for the first one? Okay. Do you think that's faster or slower than the velocity at exactly 30 seconds?
Slower.
Okay, you think it's slower? Why?
Because at 20 seconds he was going slower than he was at 30, so his time was faster.
All right. Yep. So the slope between t and 30 is flatter than the slope of the curve at t equals 30. All right. So the slope is less. Okay, so then we switch and we're like, okay, well, let's do his slope on the other side. So we do the slope before 30. Now let's do the slope after 30. So we want it between 30 and 40. So f at 40 minus f at 30 over 40 minus 30. And we're going to get some, again, nice values here. Minus 11, 13, 50. Still over 10. Big difference, negative 1120 feet per second. Okay. Is this faster or slower? It's faster, okay? Because he's moving faster at 40 than he is at 30, all right? So if we're doing the average between them, okay, so the slope between those is steeper than at just 30. Okay. So then how do we make it better? How do we make it better? So on the next page, they're saying, you know what? Let's just narrow the interval, all right? Going 10 apart, 10 seconds apart is too much, all right? There's a huge difference between negative 800 and negative 1120, all right? Let's see if we fix it a little bit by getting closer to the point that we're concerned about, all right? So they asked me to do the average velocity between 29 and 30. So f at 30 minus f at 29 over 30 minus 29. Did you get negative 944? Okay, feet per second. Okay, and they say go the opposite direction. So we'll go from 31 to 30. And that gives us negative 976 feet per second. Are these estimates better or worse? They're much better. Okay, they're much better. Okay, the reason they're much better is they're closer together. So we're narrowing in on the gap, right? We're narrowing in on the slope that we're really interested in. Okay, so they're closer together. So we're closer to the exact value at 30. Okay, how could we get an even better estimate? Yeah, just continue to narrow the interval, all right? Continue to narrow the interval. All right, so maybe we could do between t equals 29.999 and t equals 30. All right, so we just want to narrow that interval. We should get closer and closer and closer and closer to what we're looking for, okay? So now we're going to look at it in terms of some algebra, all right? And so it says we're going to find the average velocity between t equals 30 and a time t equals 30 plus h. H is some random amount that we're past 30, because to do velocity, to do slope, how many points do you need? You need 2, okay? We need 2. So let's do f of 30 plus h. That means we're going to use that function. Let me write it back down for you. Okay, f at t was 12,7,850 minus 16 t squared. Okay, so that was our function that we're plugging into. This is going to be some pretty gross algebra. All right, bless you. But it's not terrible, okay? That's why we have calculators, thank goodness. So f of 30 plus h, we're just going to plug that in. So I have 12, 7, 8, 50 minus 16 times 30 plus h, the whole thing squared. Okay, this is going to be some gross math, but we can do it. Okay, I keep 12, 7, 8, 50 minus 16 times, if I square 30 plus h, that means 30 plus h times 30 plus h, right? So I square the first, which would be 900. I multiply those together and multiply by 2, so 60h plus h squared. All right, so we're just doing some algebra. All right, you should write this down because you're going to be doing a lot of this today. Okay, and so then we continue the process of just simplifying. Okay, so 12, 7, or 127, 850 minus, if I multiply the 16, all right, 16 times, I don't have my calculator. What's 16 times 900?
14,400.
Okay, and then minus, I'm going to do 16 times 60, that'd be 0, 6, carry my 3, 960. H, and then minus 16h squared. Okay, so we're just distributing and combining all of our like terms. The only two things that I can still put together are these two numbers right here at the front. And so that's going to give me 113,450 minus 960h minus 16h squared. Okay, so that's our first expression. So what it's doing is it's leading me through this average velocity, okay? So my two ordered pairs were t equals 30 plus h and t equals 30, right? So what we just did was f of 30 plus h. Well, now we're going to do the top part of the average velocity formula, okay? So we're going to take that expression that we just found, so 113,450 minus 960h minus 16h squared, and we're going to subtract f at 30. Well, f at 30 happens to be 113,450. All right, that's not a coinky-dink. All right, so when I subtract, I'm going to lose those two terms, and it gives me negative 960h minus 16h squared. Okay. Now, the last thing it's going to ask me to do is to take what I just found and divide it by h. Now, why, because this looks like my slope formula, is it just h on the bottom?
Because h is already the difference.
Yeah, if we think about the slope formula, we would do 30 plus h on the bottom minus 30. The 30s would go away and it would leave me with just h. Okay, so that's where it came from. It was that slope formula. All right, the difference in the t values. And so now if we plug in what we have negative 960h minus 16h squared. We're going to divide that by the h, right? What's going to happen? What happens to these h's? I got to divide everything by h. Right? They would reduce out. Okay, I'd divide each thing up there by h. So negative 960h divided by h would give me just negative 960. Negative 16h squared divided by h would give me just negative 16h. Okay, now, what would we have to do? All right, so we've got a velocity formula there for some arbitrary distance, as small as we want to make it, from 30. Okay, h is that distance from 30. What would we have to do to get the slope or the velocity at exactly 30? What would have to happen to h? What do we do in calculus when we want to get really, really close to something? Yes, we're going to take a limit as h approaches 0. We want the distance away to be as small as possible. Okay, we want the distance away to be as small as possible. Well, here's our average velocity that we just did, negative 960 minus 16h. Okay, h is my variable, and so if I plug in 0 for h, I no longer need the limit. I just have negative 960 minus 16 times 0, which is negative 960 feet per second. Okay, and so that is his instantaneous velocity at exactly t equals 30, okay? We can't do velocity without two values, right? It takes 2 points to be able to do an average rate of change, but to make it instantaneous, we take a limit, right? Now, the last question it asked me is, did he go supersonic? Okay, they tell me the speed of sound is 1,125.3 feet per second. Okay, so did he go supersonic at t equals 30? No, okay? No, because it was less, all right? Negative 960, all right, not quite there, all right? So, congratulations. All right, you just did your first instantaneous velocity. All right, and that's what today's going to focus on. It's a lot of algebra. Yes, baby. All right, it's a lot of algebra, all right, to get us there. So let's take it simple. Let's start with an average rate of change, okay? Average rate of change is just slope, okay? An average rate of change is just our slope, okay? So how we normally would see it is f of b minus f of a over b minus a, because we're talking about on an interval from a to b, okay? But I'd like to challenge you to think of it in just a little different way, okay? In a way that we refer to, all right, as our 2 points of x and x plus h, okay? So let's do it on that interval, all right? What would average rate of change look like on that interval? We would take f of x plus h minus f of x over x plus h minus x, which would simplify to f of x plus h minus f of x all over h. All right, that is your average rate of change. Okay, we've got a point x. H is some arbitrary distance away. Okay, it's some arbitrary distance away. We refer to this as the difference quotient. Okay. It's just our slope between 2 points, the difference quotient. Now, when we move to instantaneous rate of change, all right, we're no longer talking about between 2 points, but we can't do slope any other way. There's no way mathematically to do it. Instantaneous rate of change is the slope of the curve at a point, okay, or the rate of change of the curve. Thank you, Carly. At a point. Now, we look at this in two different ways, okay? So let me show you the first one. This is what we call definition 1. So let's say that we've got a curve. We've got x, and then we've got the point x plus h, okay? So the distance between them is that h. And I'm trying to find the slope between those 2 points, okay? So I want the slope at exactly h. Well, we have to do a limit. So we would take the limit as h approaches 0, and we'd use the difference quotient. Okay, f of x plus h minus f of x all over h, right? The part inside is my average rate of change. When I add the limit, it makes it an instantaneous rate of change. Okay, so the difference quotient is the average rate of change. When we add the limit, that makes it instantaneous. We want the distance between them to be as close to 0 as possible. That's why we do a limit. Okay, so this is definition 1. Now, sometimes all of this with the h can just be a lot. It's a lot of algebra, okay? It's hard to do a limit with all that stuff in there. So sometimes they define it this way. Let me show it to you. So we have a point A that we start at and a point X, okay? And we're looking for the slope at A, okay? What is the slope of the curve at A, right? We always start with the average rate of change, okay? So the average rate of change between those 2 points will be f of x minus f at A over x minus A. That's the slope between those 2 points, okay? So you've got x and you've got A. In order to make it instantaneous, what do I want x to do? Because right now it's way far away from A. Thank you. Yeah. Yes. I'm like, dang, she got so pretty soft. Okay. What do we want x to do if we want it to be instantaneous? If we're looking for the slope at A. Do we want the distance to increase or decrease? I'm trying to find the slope at exactly A. Yeah, it needs to approach A. It needs to get close to A, okay? So we're going to take the limit as x approaches A. So again, this first part is my average rate of change. When I add the limit, it becomes my instantaneous rate of change, all right? These are our two definitions for instantaneous rate of change, okay? We can't find the slope at just one point. That's why we have to use average rate of change and tack on the limit, okay? So that we're closing in that distance between the 2 points. Okay. This thing might be good to put on your reference page, your red reference sheet if you've got one, all right, that you're working on. All right, so let me show you some examples, okay? So I actually pulled this from, if you go back and look at the AP Classroom video that's available for this lesson, this is from a guy who I really like. He draws great pictures and he has beautiful handwriting, but all of his problems revolve around his cats, okay? And so Kong is his cat. All right, so just as a heads up, anytime he talks about Kong, that's his cat, all right? So the altitude of Kong's helicopter is given by K of T. Selected values of K of T are given in the table above. The altitude of Estelle's helicopter, that's his other cat, is given by E of T, okay? The equation provided above. Both K of T and E of T are measured in feet, and time is measured in minutes after takeoff. Okay, so units are important. So the first thing it wants is the average rate of change of Kong's helicopter altitude over the interval from 5 to 20. Okay, so it just wants average rate of change. So what are we going to do? Just the slope. Okay, we're just going to do the slope between those 2 points. Is it going to come from the table or the equation? The table. All right, it's going to come from the table. So we're going to take K of 20 minus K at 5 over 20 minus 5. So get me a value for that. Double check my math. Okay, we'll take 3 decimal places always. So 766.667 feet per minute. All right, let's do the same thing for Estelle's helicopter. All right, what'd you get for Estelle? Yep, 625 units are important, feet per minute. Okay, so those are average rates of change. Okay, so now we flip and it says, okay, let's write an expression involving a limit for the instantaneous rate of change of Estelle's helicopter at t equals 7. We don't have to evaluate the limit. We don't have to. We just have to write the expression. Okay, so it tells us we're going to need a limit. Right? You have 2 options here. Okay, I typically take the difference quotient because that's what I'm used to. Right? So my 2 points would be 7 and then 7 plus h if I'm thinking about my interval. Okay, I'd want my limit for h to approach 0, We're plugging it into E, 7 plus H, minus E at 7, and divide it by H. And that's all it's looking for. All right? It's getting used to writing those limit expressions for instantaneous rate of change. Okay, y'all try this next one. We'll check it, and then I'm done. It's funny that they use things like artichokes. And there's problems about monkey stack of bananas. Like, they just really like to write about really weird things when it comes to AP questions. So if I want the average rate of change between 6 and 11, everything are hours after midnight. So we would do A of 11 minus A at 6 over 11 minus 6. And what did you get? Artichokes per hour. Okay, but that's a unit of measure you never thought you'd use, but there we go, okay? Artichokes per hour, right? So now we want to do an expression for the instantaneous rate of change at 9, okay? If you're thinking about the difference quotient, that would be your two x values that you're going between. So limit as h approaches 0, a of 9 plus h minus a of 9 over h. Anybody try using the alternate definition or definition 2? Okay, we could do this. We could do the limit as x approaches 9. Okay, of f of x minus f of 9 over x minus 9. That would work as well. Okay, so both definitions would work. Remember, x would be that far point. We want it to get close to 9. Okay, so if you wanted to write that down just so you have a reference, okay, to look at. Your lesson practice is just your worksheet 2.1 that was back there on the back table. There's only like 3 or 4 questions on there, just for you to kind of practice the notation. All right. Tomorrow we get into the meats and potatoes of the notation and doing all the algebra and all the good stuff, right? But today it's just understanding the notation. Your wrap-up is on Google Classroom, so let's get that done. Couple of things to note. If you wanted to retake, or if you had an option to retake quiz 1, 14, and 15, that's due by tomorrow. Okay, so just as a reminder. And if you want to do your second round of test corrections, right? Remember, those are worth 50% of the points back. That needs to be done by Friday, which is the 12th, okay? Now, I can't pass your test back so that you can peruse them and know what to go home and study, but I can tell you what you could correct, right? Like how many, if you have multiple choice, if you have free response, you can still correct. So I'm willing to do that, to tell you that, so I'll pull them up. So if you're interested, I can tell you if you want to come up here and ask me in just a second, okay? So do your wrap-up. And then look through that practice for tonight. There's only about 3 or 4 questions. Be sure you understand the notation as we come into tomorrow and get all your retakes and stuff done that you're eligible for, okay? All right, grades are up to date and all that good stuff.